Okay. So remind me, what is the, we talked last time about the fork system call. What does that guy do?
Creates a duplicate process that doesn't know that it was cloned.
Okay.
And then returns the process ID to.
Gotcha. So the fork system call, which is an actual system call, we're not talking about theoretical stuff at this point. It's going to be a Linux system call. It's a Unix-based system call that we will be using in C. And that will tell one process to clone itself. And the program pointer, so we kind of, so we were talking last time, what's a process? So we decided a process has a unique identifier, right? So it has to be uniquely identifiable on the operating system. So a process is a collection of instructions that live on the operating system that we fed on by the CPU. We talked about what's an instruction. So that's right, birds and the bees of instructions. These are great slides. How do you forget this stuff? It's because you didn't hear it from me the first time is the problem, right? I used to teach the operating systems class. Well, I mean, I'm more qualified to teach some of the upper division, and there's less programming in there. This is the programming side of operating systems. That's theoretical. Boring. I turned it into a programming class, as you might imagine.
Could make kids cry, nothing.
That's what happened when I first came here 11 years ago. Dr. Locklear had me teach 175.
Oh, gosh.
That happened once. Make that a programming class.
Poor student.
150 a programming class.
I don't have the patience for.
I think when we were taking 325, I was talking to Curcio, and I was like, well, 325 isn't going to be a programming class, is it? And he was like, well, it's a litmus class. So.
Well, 325 would be.
Yeah,
because we did assembly language stuff in there. Yeah, that makes perfect sense. All right, so last time we were talking about where do those instructions come from? When we talk about processes as being a collection of instructions, where do they come from? Well, the human being writes the high-level code because that's what we're good at. Then we run that through a compiler, which converts it into a low-level code. And then we got this couple of components in the middle, linkers and stuff like that, that translate that low-level code, which has a one-to-one relationship with the CPU, into the equivalent machine instructions, zeros and ones. So, you have this assembly language instruction, maybe it's move, M-O-V, and that's translated into machine instruction number 0001011 or something like that. And then all the parameters are passed in other, bite-sized chunks of stuff ultimately to give you a bunch of zeros and ones that you then feed into the CPU. All right, so our process is going to hold a list of instructions in machine language so that the CPU can feed off of that and perform those magic tricks, perform those operations. All right? So, process is uniquely identifiable on the operating system. It has a collection of stuff that the CPU needs to work on. Now, we've talked a little bit about multiprocessing, right? So, actually, we need to talk about multiprocessing at a little bit different level. So we talked about it for like how a web server works, where we create another guy. So, I clone myself and have somebody handle the current web request so I can go back and listen to the phone. But somewhere up here, didn't we draw a picture of two CPUs and them being scheduled? There we go. So this guy, if we have a couple of CPUs in our system and these processes are being scheduled for these CPUs, whether you have two CPUs or one CPU, in fact, maybe one CPU is the easier example to explain this. So I'll just put this back down by where our what's a process guy here. So in our older types of computers where we had a single core CPU, which technically can only do one thing at a time, what we would rely on is that our computers are fast enough that even if we had 3 programs open at once, the computer was processing them so quickly that we were convinced they were all happening at the same time. Because what happens? This guy gets a little bit of CPU time, then he's told to take a hike. Either he gets off the train when he has to hit some sort of I/O or something like that, or he's kicked off the train because he's run out of his time on that resource. Okay, so that's called context switching, right? So this guy context switches on, then when he's done, he context switches off. So we have to think about what are the, so remind me, what is context switching? What actually is happening during context switching? What is a CPU? Go ahead.
CPU's updating the process of where it finished, where like the last instruction that was run, and then taking anything out of the cache and putting new stuff into the cache. It's the next process and figures out where it needs to pick up from.
Okay, so at the very least, so now we're talking about that data structure for a process. At the very least, does a process need to remember what line it needs to pick back up on? Anybody remember what that's called from operating systems? Instruction pointer. So instruction pointer is the index of the next instruction to be dealt with by the CPU. All right, now let's take a microscope here and look at this CPU. And what does the CPU actually look like? I'm not going to get it down to like the wire level, but if we look at a CPU, this guy has a whole bunch of things that are kind of part of it. I'll draw my pretty pictures. Now, this would be a pretty old processor, but when I put things up here, oh, let's make them different colors because that's what the cool kids would do. Oh, yeah. All right, so when I put things up here like AX, BX, CX, ZX, what are those guys? Hardware registers, right? So what's a register? What's a hardware register? That's on a newer processor. Yeah, these guys are 16-bit registers with a low and high, 8 bits, 8 bits. AX, BX, they do exist on your modern processors, but more modern processors have more registers that have larger sizes. But yeah, you're right. EAX would be, they're 32-bit registers with a high and low of 16. And then you have the next level up, which are 64-bit registers and yada, yada, yada. But important thing here for us is we want to consider what's a hardware register. Somebody else. We've heard of those guys before, right? Go ahead.
Fast memory located near the CPU.
I'm good with that. Let's have, like, we're going to put really fast memory located near the CPU. So as a general rule, the closer the memory is to the CPU, the smaller it is and the faster it is. So after we get past your hardware registers, then we move into like L1, L2, L3 cache. Those tend to get bigger and bigger and bigger in size, slower and slower and slower, and farther away from the processor. And then we get to our system memory, our RAM, and compared to our hard drive, RAM is really, really, really fast. Compared to a register, RAM is slow motion. Registers are really fast, but they hold nothing, right? AX is a 16-bit register. That holds one number, and not even a huge one. That holds if it's a unsigned number that's 0 to 65,535. That's not huge values. That's really fast. All right. So that's what a hardware register is. And then so we have some other things that are also built onto the processor, like I mentioned, cache, L1, L2, L3 cache. But let's just talk about this in terms of hardware registers. So something else, when we context switch out, when a CPU or a process gets onto the CPU, he has to reload all those registers with their former values, what the values were when they left off, right? When he context switches off of the CPU, he's going to pack his bags and have to remember the current state of the CPU so that he can pick up where he left off next time. Make sense? So our process, another quiz question from operating systems. Anybody remember what the name of the data structure that represents a process is in our modern operating systems? Go ahead. No, that's part of the assembly language. Go ahead. That's the operating system itself. The word process is in it. It's 3 letters, acronym. I'm going to actually put it up here. PCB, process control block. That's the name of the data structure that holds the stuff related to the process. Okay? So that's going to be a unique identifier, an instruction pointer, current state of registers and cache, let's just say. All the stuff it needs to be able to load back onto the CPU. Then collection of instructions. And I'm actually going to say current collection of instructions because those processes do get updated, because when you have an application like Microsoft Word, do you presume that there's a lot of instructions that make up Microsoft Word? Do you think all of those instructions get loaded into a single process when it first loads? Or do we need enough of them to get the ball rolling and then have a mechanism for bringing, when you branch off, when you have an if statement and the if statement says go here, you need to be able to retrieve the new set of instructions to keep going down that path. Otherwise, your PCB would become huge, right? So we're going to have some sort of limit on the amount of instructions we can, cache a buffer at a point in time. And then we need to have a mechanism for bringing that stuff from RAM into a process. You know what that mechanism's called? Who? Paging. Paging is how things are stored in memory. So it's we're related. That's who have paging algorithms. Paging's related to it. It's called swapping. We swap things in and out of memory based on several different mechanisms. What's likely to be needed next and stuff like that. But that's where our instructions come from. We don't load the entire application's instructions into a process control block. Instead, we load what we're going to need next. And then if we need something next, it's going to be related to a specific page that lives in memory. We go and retrieve that and bring it into the process. And if it's not in memory, then we swap it from hard drive. Usually it's coming in from swap space, which is kind of fake RAM that uses your hard drive, brings it into real memory, and then we can load it into a PCB. All right? Not really important for us in here, but that's what's happening under the hood. What we care about in here is kind of the nature of our processes. Now, the reality is so we have all of our instructions. We have all the current state of the registers. This is to support context switching. Instruction pointer, this is also to support context switching. So this guy, keeps track the next instruction to be processed by CPU. Ruh-roh. Big money, big money. Did it save? Completely deleted it. Okay. So there might be some other things in there. Our process control blocks get more and more complex, especially when we start considering an operating system that has the ability to schedule for multiple CPUs. And now our process control blocks might need to hold information about other processes that maybe it's reliant on, things like that. Let's not go that deep here. Do we kind of have a decent idea on what a process is? What that data structure kind of information that guy holds. All right, so when we fork a process, we get a second PCB that has its own unique process ID that will have its same instruction pointer. It'll already be incremented to the next line we're to pick up. It will have a copy of all the current registers and that kind of jazz. again, for supporting context switching, and then it'll have the same current collection of instructions. Because each of those processes, the next time they get on the CPU, they're going to look at the exact same next line of code. And they're probably, the way typically multiprocessing works, is they will do something different depending on the next question. You typically fork, and then you say, if I'm the parent, do this stuff. If I'm the child, do this stuff. Make sense? Okay. Why is fork bad? What are some of the downsides of creating a new process control block? That's really at the crux of it. It's duplicating all the resources, right? Now, this might not seem all that impressive to us, but there's a lot of crap we're storing here, right? A lot of stuff we're storing as part of the PCB. Now, the reality is that when we think about the types of problems we're solving with multiple processes, we might not need all that information. We really kind of need things to happen in a, so we're going to say supports non-blocking processing at the cost of resources. Oh, we can just say, what is blocking? When I say a blocking instruction, what am I talking about? What does it mean for an instruction to block? Go ahead. That it does interrupt the CPU?
It does.
Okay, but if it interrupts the CPU, that indicates that nothing else from that same process can happen at the same time, right? Okay. So the idea would be, so let's give a real life example of this. So I ask you what your name is. Now, I printed something to the screen. Now I'm going to try to read in the name, right? Which takes I/O. Printing it to the screen also takes I/O. So actually, that the idea of asking a question and then for console-based programs, asking a question and reading in the answer is actually ridiculously expensive because we have to block, we have to interrupt the CPU, we have to context switch off the CPU in order to spit what is your name out to the screen. Then we get back in line, wait for the CPU again. The very next thing we do is we try to read in your answer. So we stop again, we context switch on, do one instruction, context switch off, and wait for your reply. Now, how long is it going to take for you to type your name in? You might do it right away. You might walk away from the keyboard and come back in a week. We don't know. A blocking instruction prevents the next instruction from processing. So the issue here would be if we kind of thought about that web server type of example. If he's making a request for index.html, well, he's making a request. So I pick up the phone. We start chit-chat in HTTP, right? We're talking the Hypertext Transport Protocol. And I'm waiting for his request. So I'm waiting for him to finally send me a GET. Maybe he does some of the early HTTP chatter early on. We do a little negotiating and blah, blah, blah. Then finally, the next thing that I would expect is for him to make a GET request to me. And it just never arrives. Because he's walked away. He's getting lunch. Right? He's a web browser in this case. So, web browsers eat too, people. I mean, what? What's up? They eat cookies. That's a good joke. All right, so now the issue here would be if we didn't create a new process here. If I pick up the phone and I'm the one web server process, and we started chit chat, which probably happened very quickly, right? Our early HTTP maybe was fast. And maybe we wouldn't even notice too much if there's only a couple people hitting the web server. If you and I really quickly talk some HTTP and then you ask for index.html, I spit it out, and now I'm done with you. You're browsing it on your browser and you've disconnected from me. And now I can go and serve the next person. If we only have a couple of people using the web server, that might actually be okay, as long as you're on the ball, right? Okay, but in a bad situation, if he delays that request, and I'm just hanging on the line, waiting, it's like when they put you on hold on Amazon or something like that. Okay, you're just waiting on the line for him to come back. Now she can't make her request. She can't even dial in. She's getting busy signals, the equivalent of a busy signal. All right, so what do we do? So that would be considered a blocking instruction. I am trying to read from the socket your next request, your next string that's following the HTTP protocol, and it's not arriving. I'm just waiting to read from it. Make sense? That's a blocking instruction. Our way around that is when you first dial, when you first connect in, and a socket is created, communication channel between two endpoints. When that socket is created, what's the very first thing I do? I fork a child process who takes over that socket. He's going to have that conversation with you. And when you walk away because you're getting lunch, he's delayed. But now I can still be sitting here and execute the next instruction. That makes sense? Because I spawned off a little worker bee to do that work for me. So a fork allows us to create non-blocking instructions. So we create this second process who's in charge of handling the current instruction so that the next instruction can move forward. Make sense? So blocking instruction is that. A non-blocking instruction would be an instruction that does not block, that does let us move to the next thing, that kind of stuff. If you think about it in a non-networking example, I was just pointing out a couple minutes ago, if you print to the screen, please enter your name, and then the very next thing you're reading in is, you have a scanner, input.next line or something like that. Until the person types in their name and presses enter, that line blocks. You could have 5,000 lines of code following that input.next line, and they're not going to get executed until somebody finally types some stuff in and presses enter. Make sense? Those are blocking instructions. So why is fork bad? It does support non-blocking processing, which is good. Imagine what things would be like if we didn't have non-blocking. How many applications that we have today would not work? How many things that we do on our computer would not work if we could never create non-blocking instructions? Even though we don't think about it, the idea of creating new sub-processes, child processes, regardless of how resource intensive they might be, we really, really rely on them. We go back to some older operating systems like Windows 3 that didn't support multitasking. You had one program open at a time. Why? Because whatever you were doing with that program, that was blocking the next instruction. You couldn't create another process. That makes sense? Now, there were some special cases there because the operating system had kind of it was a two-process operating system where the operating system was allowed to do its thing, and then as a user, you could do your one thing. Make sense? And then actually in some of the early Mac OSs, Mac OS 6 through Mac OS 9, you had something called preemptive multitasking. So it kind of sort of faked it. So it will allow you to kind of pause an application, whether it was in a blocking state or not. It would just kind of get put on hold and put in the background. But it was getting very, very, very little CPU time. It was basically just being kept alive. And where you really notice that with some of those older operating systems where, let's say, when the early days of the internet, when you were using something like OS 9 for a Mac, you might be downloading a file. And let's say it's downloading at 2K a second, which might have been a pretty good speed back then. and now you put it in the background because you want to work on your Microsoft Word document or something like that for a little bit, and you go and check on it, and it's slowed down to 1 bit per minute or something like that. Slowed down to basically nothing. Even though it appeared like two things were happening at once, that secondary process was getting so little love from the CPU that it wasn't actually making any progress. Does that make sense? It was just being kept alive. Because at the end of the day, what was most important? The process that the user is currently working on. So you had, in the foreground, you had Microsoft Word. You want that guy to be fast. That's not our mindset when we use computers anymore, is it? You might have 10 things going at once. You want them all to be fast. I don't care if I'm never going back to that tab on the web browser. It should be fast. You know, we look at our web browsers. We got 50 tabs open. I don't even remember how I got to that one. Right? That's a pop-up from some other screen. It should be fast. Right? Then you run into the situation where your computer starts making sounds because there's a video playing on one of your zillion tabs. Right? Actually, I'm doing pretty well on tabs here these days. Look at that. That's not bad for me. You can almost read the full word on each of those tabs. I'm like a hoarder. I never want to close a tab. You never know when you're going to need that. What's this?
1 or 2.
1 or 2?
Yes.
What, do you open up multiple browser windows?
No, just look at one window and 2 tabs. So one for my email and whatever I'm working.
So you're a single core processor type of person.
Because I will lose. I think I have to be closed.
Yes, I feel like I used to be like maybe a 64 core processor. Now because I've gotten older, I'm down to like maybe a 16 core. But I can't single task. My mind's going, I'm thinking about too much stuff. It would drive myself insane. Oh, I'm already insane, but you get what I'm saying. All right, so as you pointed out, fork is solving a real problem for us, right? If we go back to these early days of our operating systems where we couldn't have more than one thing running at once, and we needed a solution to that, fork was the solution. But it was very resource intensive. Now, keep in mind that in the early days of operating systems, when we kind of first started making that foray into multitasking-based operating systems, kind of with Windows 95, and really Apple didn't have a decent multitasking model until it stole OpenBSD Unix and put a nice front end on it to make it look like an Apple thing called Aqua, because then they got Unix's multitasking model, which was great, time tested, but they stole it. You hold that against them? I mean, why can't you support a real company like Microsoft who's never stolen anything? It's called innovation. You steal, you get sued, you pay, you settle outside of court, and you move on with life. That's the American way. Okay, so in any case, our Mac operating system today, this guy I'm using here this is Unix with the, artist's front end on it or whatever, which half the time you don't even care about. Xerox, that goes back to the first graphic user interface operating system. So Xerox Star was their code name, where they had a mouse-based thing, and they decided the real money was in printers and copy machines, not personal computers. But they've done okay with printers and copy machines. But Microsoft did a little bit better. Apple really did a little bit better. Microsoft was the real winner there, right? Because what happened? Apple really didn't steal from Xerox. Xerox gave it to them. So let's not paint them in a bad. Xerox engineers say, "Hey, we're getting out of this market. We're buddies with Steve Jobs. Let's call him in. Let's just spill our guts to Apple's engineers." Apple's engineers go back and build an operating system that's mouse-based, graphic user interface, point and click, that kind of stuff. And at the time, Apple and Microsoft were partners, right? Yeah, Apple and Microsoft were partners. The previous Apple, so Apple internally had 2 different hardware lines. They had the Apple computers and then the new Macintosh computers. So Macintosh computers used this operating system with mouse clicks, using a mouse, where the Apple computers were running MS-DOS. They were running DOS, which is a Microsoft operating system, which they didn't write either. They bought it for $50,000 from some dude who ran a hardware store, computer hardware store, way back when. Oh man, that was like the most profitable deal in history. This goes back to Microsoft. So Microsoft, Bill Gates and his cronies, they go in to have a meeting with IBM. This is way, way, way back, when IBM was the cool kid. And they're in a meeting, and this is kind of when personal computers were just starting to kind of sort of become a thing. And IBM said, well, maybe we're going to play in that arena, but they didn't want to take too much risk. And Bill Gates is sitting across the table from him and says, look, we don't want to, we have an operating system. Okay, we don't want to sell it to you. Instead, we want to license it to you on a per machine basis. From IBM's perspective, it's like, oh, that's great. We don't know if we're going to sell any machines. So we don't have to pay you a dime unless we sell a machine. Right? Great. And then IBM had a great quote. You know what that quote was? The real money is in the hardware. Software is unimportant. So Microsoft really invented two things there. Well, the main thing is they invented licensing of software, right? But it's even better. That story is even better. You know what the kicker of that story is? So Bill Gates is sitting there and saying, look, we want to license our operating system to you on a per machine basis. IBM says, yeah, no problem. Sounds great to us. Real money's on the hardware. What was the joke?
They didn't have an operating
He didn't even have an operating system. He agreed to license an operating system that he didn't have to IBM. And back then, IBM was the big, big, big dog. So that was, he was basically, that was poker face, right? He made this deal. Probably the most profitable deal in history. So he leaves. He leaves there. And they have to now go find an operating system. Okay, because they just made a deal with IBM. So he goes into this some little computer hardware shop type place, basically the old school Radio Shack type place, because the rumor was there was some guy in there who had kind of written an operating system. It's just like a hobby. I think, oh, I'm going to write an operating system. It's fun. Keep in mind, operating systems back then were, they're still complex programs, but they didn't support multitasking and all that stuff. So it was a much simpler operating system than we think about today as our operating systems. So if you did this for fun, okay, and you're still living in your grandma's basement, all right, and somebody walks in off the street, Microsoft offered them $50,000. It's like, look, we'll give you 50 grand for your operating system. What do you say? You say yes. No, this guy wasn't a licensing guy. Hey, this guy wasn't even wearing shoes. Yeah, he was wearing his only pair of clothes because he lives with grandma. Okay, and she didn't do laundry yet. And so, 50 grand back then was a lot of money. So if some random person walks off the street and says, hey, that stupid piece of software you've been writing that you wasted all your time doing, I'll give you 50 grand for it today. You say yes. But Microsoft had already decided to license that to somebody else, to IBM. Oh man, that's a deal. How did I get into that? Oh, multitasking, operating systems, Unix being better, blah, blah, blah. So fork was a necessary evil. It solved a problem that we previously couldn't solve, right? And it really opened the door for us to have multi-processing operating systems, which then made our operating systems more complex, right? Because now if you have multi-processing operating systems, now you have to have a mechanism for a process to leave the CPU so another process can get some CPU time. That's called context switching. And we've said context switching is bad. Again, it's a necessary evil. So as you come up with new things you want your operating systems to do, now you make your operating systems more complex because they now need to have the extra programming to be able to do that. Now you become more resource intensive, so you need to have faster computers to keep up and make us convinced as a user that everything's happening at the same time. And now what do we do today? We have multiple core processors where we physically can do more than one thing at a time, which makes our operating systems even more complex. Because now we need to play the game of, we're going to context switch off this CPU, and now when we go get back in line, there's 6 lines to choose from. Which line do we get into? Well, now we got to consider, well, are any of your little friends out here? Are you reliant on their computations? If so, you need to make sure you happen after they happen. Because you might try to go read a piece of memory that wasn't there. So it's this vicious cycle. Like humans want better, operating systems get more complex, possibly more bug prone, blah, 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 or possibly we need to, this goes on and on and on and on. Okay, but in the early days, we didn't even have a solution for this. That's where the fork system call came in. But most of the time when we need two processes, we need to have a non-blocking solution. We don't need all those extra resources. So this guy's very resource intensive. Now I'm going to create another slide here. It's going to say, so why is fork good? In the modern operating systems, we think about a single core processor that can only technically do one thing at a time. Yet it does, you have 10 processes lined up. It gives you this guy a little time, then this guy a little time, then this guy a little time, this guy a little time, then it circles back around, and all this stuff is happening really, 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 really fast so that we're tricked in the end to think that it's all happening instantaneously, right? What's good then about a single program creating two processes? Twice as much CPU time. Like, forget about fair. Hey, my program's more important than your program. So your program can share with all these other guys. I don't even need to have multiprocessing. Instead, I'm gonna fork a child process off so I get twice as much CPU time. Hell, I might just create 10 times the CPU time. Great. I'm the most important. Make sense? So fork actually produces higher performance multitasking for a single application at the cost of more resources. Gets more CPU time since each process gets its own CPU time. Make sense? Now, if we go to more modern, what's the more modern alternative to fork? Who? Tree? That's a made-up thing. Threads. We got this dude called a thread. We've heard of threads before? Okay, so a thread, this guy is kind of like a lightweight process. And what do we mean by lightweight process? Uses a minimal amount of additional resources, but has some catches. Shares the CPU time with the parent. Is managed / scheduled by the parent process. Okay, so if you have a parent process that spawns two threads, let's say the parent process gets 5 seconds on the CPU. It's way more than it would get, but let's just use that as our numbers. That parent process has to decide how much of their 5 seconds they're going to give to each of those processes. That make sense? So in order to support multi-threading, the PCB maybe becomes a little bit more complex because now you have to maintain kind of a set of instructions and an instruction pointer for all of your child threads, all the threads you spawned off, because you have to decide what am I going to deliver to the CPU next? Which of my threads gets CPU time next? Does that make sense? Because these guys aren't waiting in line for the CPU. These guys are waiting in line within a process for the process to say, okay, thread number 2, it's your turn to use the CPU, which we're already on. I have CPU time right now. I'm sharing a little bit with you. You do your stuff for the next 3 cycles. Thread 3, you're up next. Thread 4, you're up next. Then I'll do some stuff, and so on and so forth. In fact, actually, usually the way it works is our modern day processes, by definition, are defined as a single thread. So it's actually a process that wraps around a thread, and it schedules for that one thread. And then once you have a second thread, now it has a schedule between those two threads, so on and so forth. Okay, so threads do not suffer from context switching, because for one thread to move on to the next thread, we're not context switching. You might be doing some of the pieces of context switching, but you're not having to pack all your bags. Make sense? But now the downside to threads is you get less processing power, because you still get the fixed amount of CPU time that the parent process was getting. Now you're just sharing it among a bunch of threads. Having multi-threaded applications allow us to write non-blocking applications, because technically it's not blocking, because your thread will get a word in edgewise next time the parent allows it to get some CPU time. But you're still sharing the parent's thing. So it allows you to create non-blocking applications without having a larger resource footprint in the operating system. Make sense? We will initially be using fork because it has some historical significance, and it's still around today. If we want more processing power, we use fork. All right? Questions, comments, concerns, bribes? We are almost at Cloud 9 now. So hopefully next time we'll be writing some C code in Cloud 9, and then maybe we'll get to write a web server over the weekend. Well, I say we, I mean you. Yeah. That's right. All right, I'll see everybody on Friday.